This is a walkthrough of a couple of the questions from the worksheet we did in class last week. It was similar to the questions at the end of the week on the quiz that a lot of people didn't know how to do. So I thought I'd post some solutions to these two and then give you some more problems to try. So in these problems, what we have is a population parameter proportion. So that'll be denoted P. That's given to us, and we're asked about the p-hat distribution. That is the distribution of of sample proportions that we would get if we randomly sampled over and over and over again, the same way that we rolled dice in class, and everyone rolled their own dice, so everyone had their own sampling p-hat. And so we're talking about the distribution of those p-hats. And so the theory tells us that the p-hat is going to be centered at the true mean. So I'm just going to round these off to 2 decimal places. I have more decimal places to put in my calculator, but when I'm labeling this thing, it's hard to write 4 decimal places without getting crowded. So so the center, hang on. This is not a good day for writing on this thing. Let's see. Center of the p-hat distribution. So in other words, the sampling distribution is centered at the true proportion. And again, you may think, well, how would we ever know what the true proportion is? And so you can think of this as either a theoretical or hypothetical true proportion, and it's fine. So in all these problems, it'll either tell you a proportion based on theory or a proportion based on an assumption. That's fine. But that's the center. The standard deviation is given by this formula. So it's p times 1 minus p divided by the sample size. So in this case, it's the square root of 0.5556. Well, that's not going to fit. So square root 5556 times 1 minus 5556 divided by sample size here is 50. So make sure all of that's inside the square root sign. And if you do that correctly in the calculator, you'll get approximately, oops, now my calculator turned off, hang on, 0.0703. So again, keeping everything to 4 decimal places for my calculations, but for my labels, I certainly don't want to try to keep track of that much accuracy. So one standard deviation is going to be 0.63. That is the center plus 1 standard deviation. The second tick mark here is going to be at 0.70. That's adding another standard deviation. In this direction, I'll have 0.49 and 0.42. Again, just labeling with 2 decimal places just because I need a sense of scale, but for my exact calculations, I'm going to use these answers to 4 decimal places. So that's what it looks like. Now, on the worksheet, I had a smaller probability in here, and it caused some confusion because right away the probability that I gave did not really fit on the picture very well, which is certainly possible. That happens. It indicates a rare event, but it's not the best choice for a first example. So I changed it here to be, let's find the probability that p-hat's less than 0.5. Now remember, this is the distribution of p-hat. So if everybody did their separate samples of 50, everybody's sample proportion would be somewhere on this distribution. And so what's the probability that your particular proportion that you got was less than a half? Well, we can find a half on here. It's somewhere about there. Why don't you look at your scale down here and figure out where 0.5 would be. And it says, what's the probability that p-hat is less than 0.5? So a p-hat of 0.49 or 0.42, right? These are all p-hat values. These are all less than 0.5. So this is what my picture would look like. The probability of p-hat being less than 0.5 is just the area of this shaded stuff. Now, I need to use my table or my normal CDF function to find the area, but to do that, the way we've been doing it is to translate this picture, the p-hat distribution picture, over here to the z-score picture. And to do that, I need to know what the z-score is of this line that I drew. That's the only thing that I need to know. The line is somewhere here, right? I know about where it goes. So the shading is going to be over here. These two pictures should be the same shading. The only difference is the scale at the bottom is different. On the z-scale, the z-score scale, my tick marks are literally just numbered by the tick mark. So 0, 1, 2, 3, negative 1, negative 2, negative 3. You're just putting the numbers on, numbering the tick marks up and down from the mean. So the key is, what is this z-score? And so the z-score that you get here, you get from this picture by taking the value you care about, 0.5, from the mean, is 0.5556. So the value I care about minus the mean divided by the standard deviation. And if I do that, I get approximately negative 0.79. Now this value we want to 2 decimal places because that's how our table is organized. Our table only gives z-scores to 2 decimal places, so I want to make sure I get 2 correct decimal places here. So that's the z-score. And you see it's between it's between 0 and negative 1, which is what it looks like should happen based on this, and that's what's happening over here. So that seems about right. So this probability then is the same thing as saying what's the probability that z is less than negative 0.79. And so on lots of the previous videos I've used the table for this. Let me just write down what the calculator function would be for those using calculators. So this is our normal CDF function, and I'm going to the normal CDF function takes 2 arguments. The arguments are where should you start shading and where do you stop shading. So we're looking at this picture now. I stop shading at negative 0.79, right? We think of starting and stopping as being left to right. We always read a number line left to right. So we're stopping our shading at negative 0.79, but we're starting our shading forever, basically. So forever out this way. So we talked in class about, this is negative 3, so if you go out to like negative 10, for all intents and purposes, that's forever. If that bothers you, go to negative 100 or negative 1,000. Anything you put in that's way, way, way off the screen to the left will be okay. So the function function called normal CDF negative 100 comma negative 0.79 is going to give you the area out from negative 100, which is way the hell out here, all the way up to negative 0.79. So that will be the answer to C. So that means that whatever this number is, that percentage of the time, I guess I can figure it out. So on my calculator, I got that this is approximately 0.2148. So that's the probability. So that means about 21% of the time, if you really did this exercise, if you really rolled 3 dice and looked to see when you get 3 different numbers, that about 21% of the time you would get a p-hat in that experiment that's less than 0.5. So that's our probability. So let me run through the answers to the next question. I won't go through this much detail again, but just if you want to try the one with the batting average, we can check answers. So the first step is to draw a sketch of our distribution. So remember and I'll keep 3 decimal places here just because it's batting averages, so it's easier to look at. So the center of our p-hat distribution is the theoretical proportion. So we think of this as the true proportion in which he gets a hit, so 0.296. And we think of a sample as drawing 500 random values, where each time he has a 0.296 chance of getting a hit. And so if we do that, we can get the standard deviation. So the standard deviation, again, is that same formula. It's the p times 1 minus p over n. It's going to give us our standard deviation of this p hat distribution. And so in this case, when I put the numbers in, I get 0.0204. That would allow me to write down some tick marks here. So let me just put one in each direction. So let's see, so 2 standard deviations above the mean. So this tick mark here will be 0.337, and this tick mark down here will be, this one will be 0.255. And so that gives me a pretty good sense of scale. And so in particular, when I see the question is, what is going to be the probability that p hat's greater than 0.330, I can see that 0.330 is about here on this scale, and we want to know the probability of getting a sample proportion that's bigger than that. So this is the probability that Andrew McCutcheon would have a batting average of 3 or higher than 0.330 in a given season. And so we can see that that's somewhere between the first and second tick mark. When we move this over then to this picture, we need the z-score for this value. And remember, the z-score calculation is the value that you care about minus the mean. So that's 0.296. That's hard to read, but divided by the standard deviation. So those numbers, the mean and standard deviation, are referring to this picture, right? So we just said the mean was here, and we said we marked off tick marks by standard deviation. So we must know the mean and standard deviation to draw this picture, and that's all that goes into the z-score calculation. So if you do that, this becomes like 1.67 is the z-score. Of course, it should be shaded, and the shading should look exactly the same as the other picture. So now to answer the question, I need to know the probability that p hat's greater than 0.330, and so on my calculator I can do normal CDF. The shading starts at 1.67. Remember, I'm going left to right, so the shading starts here. This is the left-hand side of this shading, and I'm going to shade this way until forever, basically. And so again, forever should mean a number like 100, right? But now it's positive 100 because it's forever this way. In the previous problem, I needed to start out here forever, so I said negative 100, that's forever out to the left, up to negative 0.67. So if I do this value for my calculator, I'll get 0.0475, basically. So less than a 5% chance. So from a probability point of view, there's less than a 5% chance that Andrew McCutcheon would hit 330 or more in a 500 at-bat season. Now, if you're using the table for these problems, just very briefly, remember that the table actually gives you answers directly to questions like this. If you look up negative 0.79 in the table for your z-score, the area you get is going to be about 0.2148. So that's going to be exactly, looking up negative 0.79 as a z-score, the table value is going to be 0.2148, because the table gives you areas that look like this, things that are shaded to the left of a line. This is not what's going on in this problem. We don't want the area shaded to the left of this line. We want the area shaded to the right of this line. So if you look this up in the table, it's supposed to be like a star. That's terrible. If you look up 1.67 as the z-score in your table, you're going to find that the area of the white region that you see there is going to come out to be looks like 0.9525. So if that's the value you get, because you're using a table, you have to remember that that's not the area you want. That's the opposite of the area that you want. And so to get the actual answer to the question, which is over here, you would need to do 1 minus the 0.9525 that you got from the table. So pay attention to that if you're using the table.